Welcome everyone. So my name is Krzysztof Sarwa. I am application engineer at ONT, as well as programmer at AGH Marine Science Club. And today I'm going to present you how we developed our solutions for vision system and robot control. As a science club, we are building underwater robots since 2018. Our first project was remotely operated underwater vehicle. And right now we are working on autonomous underwater vehicle named Haller. While creating our robots, we design most of the things ourselves and try to introduce new and innovative ideas. We have designed the entire structure of the robot, its platings, electronic diagrams, a new drive system that uses less energy, and thrusters that are more effective than most of these available on the market. The testing ground for our robot will be RoboSub competition, in which teams from all over the world will compete. And our robot will have to complete tasks such as identifying and swimming through the gate, finding objects and hitting them or shooting the torpedoes, placing items in appropriate bins, finding path with visual or hydroacoustic markers, and emerging in appropriate zone. As it is an autonomous robot, it must be able to recognize objects in its environment and make appropriate decisions based on them. And we decided to base our solution on the capabilities of stereoscopic camera Z2. This camera has wide view angle of 120 degrees and two lenses 12 centimeters apart, which enable spatial vision. This camera also has the ability to perceive depth in the image, as well as create 3D map of the environment in the format of MEF or cloud of points. To detect object, we use YOLO V4 neural network. The full name of this network is You Only Look Once. And this network not only recognizes objects in the image, but also marks them with their labels. A model of this network is available on internet and is trained to recognize 80 different objects. Using transfer learning, it's pretty easy to teach network to recognize new objects, but you will also need your database. The underwater environment is quite demanding, so collecting thousands of images would be hard and time-consuming, and that's why we decided to create our own underwater image generator. So we designed a swimming pool and the obstacles, effects such as light scattering, caustics, and waves of surface. However, to not take all these images by hand and label them manually, we also implemented actions that randomly move the camera and the objects, set different visual parameters, create bounding boxes around the objects, and then save all this data to files. So the first step was to create 3D models of the pool and the objects to be recognized by the YOLO V4 network. And for this, we used 3D modeling program Blender. So our program includes a model of an Olympic pool and selected obstacles from RoboSub competition. And selected obstacles are entrance gate, path indicator, 2 boyas with pictures, and 2 shooting targets. This program also enabled to texturing and create materials for the surface of the objects. And with these tools, it is possible to create realistic-looking objects. So the creation of real underwater image required the reproduction of effects such as light scattering, limited vision range, waving of the surface, and caustics, that is, beams of focused light rays. And this was done with the help of numerous graphical tools available in Unity. So the scattering of the light and limitation of sight range was achieved thanks to the object called volume. This object allows you to define the space inside which a camera image is modified in the given way. So we already have models and visual effects. but it is also very important that our database is as diverse as possible. And this is provided by the subsystem of dynamic change of the environment and movement of the objects. So the first part is responsible for changing the graphic parameters of volume objects, and modified effects are fog build-up distance. This is how far from the camera fog reaches its maximum density, color of this fog, the intensity of the filters to blur the image, color of these filters, field of view, and few others. So the script responsible for dynamic change of the environment randomize the value of 9 parameters. And the second part of the subsystem is the script responsible for moving the camera and placing objects in the space. So YOLO network requires specific labeling and data ordering. And this is, each image is assigned one text file with the same name. There is only one line per object in each file. Each line is in the format class center X, center Y with height. Center X, center Y with height are coordinates normalized to the range from 0 to 1. And class is the index number of the object class as defined in the configuration file. In addition, there is requirement for storing data into folders. So images and text files must be in 2 different folders named images and labels. So our visual underwater image generator must meet all these requirements. And just in case, if some photos are badly labeled, there is an application in MATLAB called Image Labeler, where we can create new labels easily. Also, in this application, we can load our labeling algorithm, which is very helpful when we want to expand our database, because as labeling algorithm, we can use our trained model and then label new real images. Another application is Deep Network Designer, when we can import our network and visualize it. We can easily make changes by dropping layers from the menu. Then we can analyze these networks to check if everything is connected correctly and is working fine. Finally, with the Experiment Manager, we can define many training and experiments to find the best hyperparameters for our model. And at the end, we wanted to implement our solution on NVIDIA Jackson Xavier, but we couldn't get one due to market shortages. But MATLAB also can help here, because in MATLAB we can generate code for embedded system, which can save a lot of time and help avoid rewriting errors. So the next step was to create simulator where we can test our vision algorithms and robot control. And this program has to meet assumptions, operate smoothly and without delays in exchange data, realistically reproduce underwater image, and send or receive data from robot's operating system. We also created user interface for the simulator in Unity, and it consists of menu where we can configure options such as setting the IP address, renaming the topics responsible for receiving control command, image transfer, and current position. We could configure frequency of the messages and setting the resolution of the images. The option for changing the frequency of broadcasting and resolution of the image was implemented to allow the simulator to run smoothly on weaker computer or with the slower internet connection. Our visual simulator consists of the same 3D models and objects that were used in generator. And these are 3D models of the pool, 3D models of the objects, volume object with underwater effects and filters, object of the water surface with fader, and light with caustic effects. So resulting image is similar to those in generator, but the main difference is that in the term of the simulator, that is that the parameters of the underwater image do not change, and and objects placed in the virtual pool do not move. The robot operating system was created on the basis of ROS library. The full name of this library is ROS operating system, and the simulator must establish a connection with it in order to exchange data on the current and target position of the robot and to send the images from the camera. And for this, we use ROS-TCP endpoint and ROS-TCP connector packages. The first of these packages, ROS-TCP endpoint, is part of the robot's operating system and creates server available on local network. And the second one, ROS-TCP connector, is package of extension for Unity and allow the engine to connect to the system and exchange messages in ROS-compatible format. And the topics in our system that we are using are sim current position. This is current position of the robot in the simulation, transmitted in the form of Cartesian coordinates in the northeast down format with frequency of 10 Hz. Sim target position is topic transmitting successive target coordinates in the global system. Sim delta position is topic that communicates target coordinates in the local robot system. Sim depth is grayscale image imitating the depth perception of the stereoscopic camera, and sim image is color image from the camera. So our robot has stereoscopic camera Z2, which has two lenses. The comparison of the images from the left and the right allows the camera to calculate distance to the objects. In simulation, the robot also has two cameras, but they are function a little differently. So one is for recording color image, and the second one is for grayscale image, where the pixels farther from the lens are darker, and pixels that are closer are brighter. However, this grayscale image do not show the key information about the distance, and it is only a visualization. That camera, through its API, creates a matrix of the same dimensions, in which each cell contains a number telling how many meters from the camera a given pixel is. So in the simulation, it would be impossible to display such a matrix as an image, because if something is, for example, 300 meters from the camera, the pixel value would exceed the maximum value of 255. Therefore, it was necessary to implement a script that calculates the distance and to the object and present in the same format as Z2 camera. The ROS package for digital image processing and robot control is robot decision-making system. During its operation, it collects information about current position, images from the camera, and readings from the YOLO V4. And based on these, decisions are made, and subsequent commands are executed. An overlay on the image displays the information we need and make it easy to test our program. So the red rectangle in the middle visualizes the acceptable tolerance. So when the center of the object is inside this rectangle, it means that object is detected and is in current position in relation to the robot. And at the top, it is described whether the object is found and with what accuracy, or whether it is searched. And at the bottom, there is information about position of the object and the distance from the camera. For ROVs and AUVs, performing tasks such as construction, operation, and other highly maneuverable activities, an important factor that greatly impacts the performance is ability to move in all 6 degrees of freedom. And to achieve this effect, most ROVs use system of 8 thrusters or a less popular system of 6. And these systems are not optimal and waste a lot of energy, with many forces canceling each other. Our team was developing a project for which low and optimal energy consumption was crucial. So to lower the number of high-power motors and to eliminate force cancelling, we developed a system with 5 thrusters, which 2 were azimuthal, ones that can rotate. And they perform thrust vectoring and generate force and torque in different directions. But how did we know at this stage of the design that this drive system will work at all, and how should we control it? And MATLAB and Simulink are ideal for rapid prototyping of algorithms, and so it was in this case. But first, let's see how the system works. So it seemed to be pretty easy, but in fact, each of these activities is very complex. So first, we set the location for robot to move to, and we get feedback from previous position from sensor or from mathematical model. Then we calculate error with different techniques and merging it with LQRK matrix. Next, the needed forces to achieve desired acceleration, velocity, and position is calculated. The force is allocated to all thrusters, and the angle of rotation for azimuthal is calculated. And control signal to thruster is sent to mathematical model or to physical robot, and the cycle repeat. And now let's check the actual representation of the problem in Simulink. So this is the view of subsystem, which calculate control signal needed at each thruster. Analyzing various algorithms, we decide to use linear quadratic controller. So the current position multiplied by the gain of the regulator is subtracted from the set position, and this error goes to thrust allocation subsystem. Thrust allocation is an issue consisting in the transformation of the desired forces and moments acting on the robot into signal controlling operation of the thrusters. In our case, we also needed to calculate the angle by which the azimuth thrusters are to be rotated, which, as it turns out, is not such a simple task. Because in the classic systems without azimuth thrusters, it is enough to perform a few matrix multiplications. But here it is necessary to apply optimization by the quadratic programming method. And this happens in a block that reads the parameters regarding the thrusters and their position on the robot, and then calls the function written in MATLAB. And here is presented subsystem that contains the mathematical model of the robot. It calculates how the forces and moment acting on the robots affect its position, orientation, and speed. To calculate the entrance to our system, we need to combine 2 types of forces and moments. Both those generated by the thrusters and those created naturally as a result of the interaction of force of gravity and buoyant force. A structurally significant property is that the robot has center of buoyancy slightly above the center of gravity to ensure the stability of the structure, and that its buoyancy is slightly positive. Then, in the event of the failure of the drive system, the robot will surface after some time, and which will facilitate its extraction. So the subsystem created here is virtual twin of our structure, and it allows us to test its behavior and tune the control system without having to transport all the equipment to the pool. And the final advantage of the Simulink is the ease of connecting with robot operating system. All that is needed is a single block, which sends the simulation results on a topic, and another software can subscribe and receive the messages. So having these innovative solutions, vision, control, and drive systems on board of our robot, we will be able to perform all complex tasks without any problems. So thank you for your attention, and feel free to ask questions. Also, of course, if you have any additional question about the presentation, you can contact me by my ONT email, or you can contact our science club, and the emails are displayed on this slide.
Yes, thank you very much. I remind you that you can send questions directly on Discord chat, or you can just raise your hand. Do you have any question? Oh, here.
So in this project, you've got 5 thrusters, right? Is it possible to build robot with only 4 thrusters, so 3 for this direction up and down and 1 for turning?
I think that's not possible because with 4 thrusters you can get all 6 degrees of freedom. That's because you have to go in direction X, Y, Z, roll, pitch, yaw. And with 4 you can't get all of this.
Do we have any additional question? Okay, I'm coming there.
Okay, I have a question that you were showing pictures with really clear water in swimming pool, but what with real environment like lakes when you don't have that kind of water?
Okay, so this project and simulation was created specific for RoboSub competition. And maybe in the future, if you want to create another project, we will create another simulation of like lakes or rivers.
Thank you for answer. Any other questions? Okay, so here we have, okay.
Do tests were in swimming pool or in virtual environment as well?
So right now, most of the tests are in virtual environment. And also we still didn't test on real images. But we are in the process of collecting real images, and then we have to label them. And this is where we will use MATLAB image labeler. And we will use our trained algorithm, our model, to label new images and then test on these images. Also, control system, yes, we have some problem because we still can't get NVIDIA Jetson. So right now it is more like remotely operated vehicle because we have to control it through our computer on the ground. But in the future, when we will have NVIDIA Jetson, we will test it in swimming pool.
Oh, okay. So I have one more question. How do you determine your location underwater?
Okay, so localization underwater is pretty hard because systems like GPS don't work underwater. So we use depth aware sensor, and it is Doppler velocity logs, which estimate velocity in relation to bottom sea by sending acoustic waves and measure the frequency shift. And by this we can calculate our speed and orientation of the movement.
Thanks for clarification. And I have a question regarding image generation, because how fast you can generate it? How does it work? What it depends on?
So for now, it will be 500 images with their labels per minute. And maybe in the future we will try to increase this number.
Do you have any idea how to make it faster, or it's just on the phase of concept currently?
Mainly it depends on the computer, because if you have slower computer, it also will work slower. But also we have maybe make some optimization in our simulator.
Thanks. And additional question, I can see it here. How many photos have you used for training and what is the accuracy of your network?
For now, we use only 3,000 images for the training, but it's because if there is too many images, the training getting too long. And for object detectors, metrics like accuracy aren't used, and it's rather mean average precision. And for our model, the score is around 0.8. But in the future, maybe if we get better computer, also we have expand our database with real images.
Thanks for your answer. We still have time, so I encourage you to send questions through Discord. And the next question is, how do you communicate with the robot? How complex is this issue regarding communication?
Actually, at the end, we won't communicate with our robot because, for example, in case of remotely operated underwater vehicle, there is cable line that connects robot with ground station, and on ground station you can see images from the camera and control the robot. But in the case of the autonomous underwater robots, usually you only program them to perform some task, and then you can see the results after you pull robot out of the water.
And can you see the image from the camera in real time when working with this robot? Or how does it work?
So right now we can, because we don't have any Jetson, so we have to connect to the robot. So right now we can see the images, but in the future we will see after the end of the mission.
Thanks for clarification. Do we have any additional question here in room? I don't see any questions, so I would like to say thank you very much for your presentation. If you have any other questions, please contact our speaker directly at these email addresses, or you can always send question to our Discord chat, and we will send it to you and ask for any information.
Okay, thank you very much. We also still are in front of the entrance with our robot, so if you have any more questions, you can just come to us.
Yes, the only chance to see this robot during Test Day conference today in main hall.